Okay, so I want to talk about springs today. What I have in picture 1 is a block attached to a spring, just on a horizontal table. And it is just chilling there. I'm going to sort of denote this line that it starts at. This, we're going to say it's x equals 0. So it's at its equilibrium point. So, right, all springs just have a natural rest length, and we call that x equals 0, and that's its equilibrium. So if I now stretch it, and sometimes we just call this x, okay? Or sometimes we call it delta x. But the point is that we want to stretch it to here so that it has been displaced from equilibrium, okay? And what does this block want to do, right? When I let it go, it feels a force from the spring that way. The force from the spring is that way. And that magnitude of that force, so it is proportional to the spring constant, so just sort of a measure of how stiff the spring is, times the displacement from equilibrium, okay? So that's magnitude. But this force that the spring exerts is always opposite of the displacement. And that's why we have this negative sign. This tells you it's a restoring force. That means it's a restoring force. So this is really a vector equation, okay? Sometimes they'll just write Fs. Sometimes they'll just write it without the vectors. And sometimes it'll just be x instead of delta x. But the idea is that if my delta x is that way, my Fs is that way, right? Because it just keeps wanting to go back to this equilibrium point. That's what a restoring force means, okay? This is for an ideal spring. And when I say this, I mean the fact that the spring force is double if I displace it double the distance. And so this ideal spring, this is called Hooke's law, okay? Now, guess what? The spring force is a conservative force. So anytime there's a conservative force, it's going to have something associated with it. And that thing is energy. Okay? So, what is the associated potential energy for the spring force? Right? Sometimes you would just call this elastic potential energy or spring potential energy. As a variable, it would just be like U sub S, okay? So how do we even calculate potential energy, right, for that associated force? So hopefully you remember that we have to do the work done by the spring, right? Right, and that's going to be equal to negative delta U. Remember, this is the work done by the conservative force is equal to negative of the change in potential energy associated with that force, okay? So work done, right? Oh, it's just like Fx, right? Or is it? The force is not constant, right? F is negative kx, right? So if we actually calculate the force, we have to do an integral. And that work is going to be f dx, and so it's xi, xf, and we've got a negative sign in here, and that's important. You keep it, okay? So negative k comes out, and all right, I'm going to give you a second to solve that while I move to the page because I ran out of room. All right, and hopefully you realized it's negative kx squared over 2, and this is evaluated at xi to xf, right? All right, so let's keep going. Apparently I'm writing in an eraser now. Let's try that again. Boop. So we have negative k over 2 xf squared minus xi squared. So I'm going to write this as negative 1/2 kf xf squared minus 1/2 k xi squared. Okay? And what do we know? This was the work done by the spring, and it's supposed to be equal to negative delta U. So that must mean that our spring potential energy has this form, okay? And you've seen this before because, you've just done this before. But maybe you didn't know that it was actually a derived thing, because here's the deal. It was 1/2 kx squared because the associated force was negative kx. By the way, you should make sure that, right, we did it right, because this should still be true, right? Du dx is kx, and there's a negative sign, so yay, boom. But this is for an ideal spring. So, you might have situations where your F, is proportional to, x cubed. And then what's the associated potential energy for that? So those are the kinds of things that, you get to deal with in this class, because calculus now. You can deal with non-ideal springs, things that don't have that nice F is proportional to X behavior. Okay, one thing I want you to make sure that you keep in your intuition is things want to lower their potential energy. Remember that? All right, so if the potential energy for a spring is 1/2 kx squared, then how is it going to lower its potential energy? Right? To lower potential energy, that means that you would have a lower x, which means closer to equilibrium, right? And that's a restoring force. Yep. So perfect. By the way, the work done during that process, that work when returning, is positive. Okay, and remember that's the work done by the spring, right? The work done by the spring was negative 1/2 k x final squared minus 1/2 k initial squared. So when it was returning, x final, right, is less than x initial, which makes this whole quantity negative, which makes this quantity positive. So remember, I'm always going to try to make sure that you're working on that intuition for work and potential energy. All right, well, this is a good place to stop with this one.